Introduction in the vast landscape of human knowledge, there exist shadowy frontiers where our understanding falters and our most brilliant minds stand humbled. These are not simply questions awaiting answers, but profound mysteries that challenge the very foundations of our reality. I am your guide today on a journey through science's most perplexing enigmas, problems so fundamental, so bewildering, that solving any one of them would transform our understanding of existence itself. What makes these problems so captivating is not merely their difficulty, but how they reveal the boundaries of our knowledge, where the map of understanding ends and the true wilderness begins. Science progresses not only through what we discover, but through what we realize we don't know. Each unsolved problem represents a doorway, a portal to deeper understanding that remains tantalizingly locked. Today, we'll venture into physics, where the fundamental nature of reality eludes us. We'll explore biology, where the miracle of consciousness defies explanation. We'll touch upon mathematics, where seemingly simple questions have stumped generations. And we'll gaze into the cosmos, where the beginning and end of everything remain shrouded in mystery. These aren't just academic puzzles, they are the horizons of human thought, the questions that wake scientists in the middle of the night with both dread and excitement. Let us begin with a startling revelation. Everything you can see, touch, and detect with our most sophisticated instruments accounts for merely 5% of the universe. The remaining 95%, a cosmic shadow realm we call dark matter and dark energy. Dark matter, invisible, untouchable, yet betraying its presence through gravitational effects on galaxies and galaxy clusters. Without it, galaxies would tear themselves apart, spinning too fast for visible matter alone to hold them together. Equally baffling is dark energy, a mysterious force driving the accelerating expansion of our universe, pushing everything apart with increasing speed, defying the gravitational attraction that should be slowing cosmic expansion. Despite decades of searching, we've never directly detected a single particle of dark matter. Our most sensitive detectors, built deep underground to shield them from cosmic radiation, have remained stubbornly silent. Some theorists propose exotic particles that barely interact with normal matter. Others suggest modifications to our understanding of gravity itself. A few whisper heresies that perhaps dark matter doesn't exist at all, that our fundamental theories are simply wrong. Meanwhile, dark energy presents an even deeper puzzle. Is it the energy of empty space itself, a fifth fundamental force, or evidence that Einstein's general relativity breaks down at cosmic scales? The answer remains elusive, hiding in plain sight across the entire universe. Equally vexing is the quest for quantum gravity, the holy grail of theoretical physics. For over a century, two revolutionary theories have transformed our understanding of reality: quantum mechanics, governing the subatomic realm, and general relativity, describing gravity and the cosmos. Both theories work with extraordinary precision in their domains. Yet when we try to unite them, to understand gravity at the quantum level, they become incompatible, speaking different mathematical languages. This isn't merely an aesthetic problem. Without quantum gravity, we cannot truly understand black holes, the Big Bang, or the ultimate nature of space and time themselves. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings, with different vibration patterns creating different particles. These strings would dance in 10 or 11 dimensions, most curled up so tightly we never perceive them. Loop quantum gravity takes another approach, suggesting that space itself is quantized, built from discrete units at the Planck scale, some 10 meters across. Both approaches make profoundly different predictions about reality, yet experimental verification remains beyond our technological grasp. The energies required to test these theories directly would need a particle accelerator the size of our galaxy. Now let us turn inward to the greatest mystery housed within our own skulls: consciousness. How does a 3-pound organ composed of ordinary matter generate the extraordinary phenomenon of subjective experience? This is what philosopher David Chalmers calls the hard problem of consciousness. We can map neural correlates, identifying which brain regions activate during specific experiences. Yet this doesn't explain why these physical processes generate subjective experiences at all. Why does the firing of certain neurons produce the sensation of seeing red? Why does another pattern create the feeling of pain? Why is there something it feels like to be you? Reading these words right now. Theories abound. Some suggest consciousness emerges from complexity itself, a property that arises when information processing reaches a certain threshold. Others propose it's fundamental to reality, perhaps related to quantum effects in neural microtubules. Integrated information theory attempts to quantify consciousness mathematically, suggesting it emerges when information is integrated in complex ways that create more than the sum of their parts. Yet we remain haunted by questions. Could a sufficiently advanced computer be conscious? Where along the evolutionary timeline did consciousness first appear? Is consciousness unique to humans, or do other creatures experience their own versions of subjective reality? Equally enigmatic is the origin of life itself, the transition from non-living chemistry to the self-replicating, metabolizing, evolving systems we call alive. Darwin's theory brilliantly explains how life evolves once it exists, but remains silent on how it began. We know life appeared on Earth remarkably quickly after conditions became hospitable, suggesting the process might not be extraordinarily improbable. Yet reproducing this transition in the laboratory has proven frustratingly difficult. The RNA world hypothesis suggests RNA molecules could have served both as genetic material and as catalysts for their own replication before DNA and proteins evolved. Alternative theories propose metabolism came first, or that life began near deep-sea hydrothermal vents where chemical energy abounds. Let us now venture into the realm of pure thought, mathematics, where some of the most profound unsolved problems reside. The P versus NP problem asks a deceptively simple question. If a solution to a problem can be quickly verified, can the solution itself be quickly found? For instance, it's easy to verify whether a proposed solution to a Sudoku puzzle works, but finding that solution from scratch is much harder. If P equals NP, if every problem whose solution can be quickly verified can also be quickly solved, the implications would be revolutionary. Almost all encryption would become vulnerable. Optimal solutions to complex problems from protein folding to economic resource allocation would suddenly be within reach. So important is this problem that it carries a $1 million prize for its solution. Yet despite decades of effort, it remains unresolved. Most mathematicians believe P does not equal NP, that some problems are inherently harder to solve than to verify, but proof eludes us. The puzzle illuminates a strange truth. We often cannot prove whether problems we cannot solve are genuinely difficult, or if we simply haven't been clever enough to find efficient solutions. This mathematical mystery has profound philosophical implications about the nature of creativity itself. If P equals NP, could a computer generate the next great novel or symphony simply by verifying whether candidate works meet criteria for greatness? Equally mysterious is the Riemann hypothesis, a conjecture about the distribution of prime numbers that has resisted proof for over 150 years. Prime numbers, those divisible only by themselves and one, are the atoms of arithmetic, the building blocks from which all other numbers are constructed. Yet their distribution seems almost random, following patterns we can observe but not fully explain. The Riemann hypothesis would confirm a deep pattern in this apparent randomness. If proven, it would resolve countless other mathematical conjectures that depend upon it. Like a keystone supporting an arch, this single conjecture upholds vast segments of modern mathematics. Now let us lift our gaze to the cosmos and its most profound mysteries, the beginning and end of everything. The Big Bang theory successfully explains much about our universe's evolution, but falters at the very beginning. Travel back 13.8 billion years, and our equations break down in a singularity of infinite density and temperature. What triggered the Big Bang? Was there something before it? Did time itself begin at that moment? Was our universe born from a quantum fluctuation, a bubble in a larger multiverse, or something even stranger? Equally enigmatic is our universe's ultimate fate. For decades, cosmologists debated whether the universe would eventually collapse back upon itself in a big crunch or expand forever, thinning out into cold darkness. The discovery of dark energy transformed this picture, suggesting an accelerating expansion that might eventually tear apart galaxies, stars, planets, and even atoms in a big rip. Others propose a big freeze, where entropy reaches its maximum, no new stars form, and the universe becomes an ever colder, ever darker place. Some speculative theories even suggest cyclical patterns, where new universes are born from the ashes of old ones. As our journey through science's greatest unsolved problems concludes, we're left not with frustration, but with wonder. These mysteries are not failures of science, but invitations to deeper understanding. Each represents a horizon, a boundary where current knowledge ends and new territory awaits exploration. The history of science teaches us that today's unsolvable problem often becomes tomorrow's foundational insight. What makes these problems so captivating is not merely their difficulty, but their fundamental nature. They probe the very essence of reality, consciousness, mathematics, and existence itself. Which of these mysteries speaks most deeply to you? Perhaps dark matter and energy, those invisible presences shaping our cosmos. Or consciousness, the inexplicable miracle happening within your mind right now. Maybe the mathematical puzzles that suggest profound truths about reality itself. These questions remind us that science is not a completed edifice, but an ongoing adventure, an endless frontier where wonder and knowledge grow together. The universe is not only stranger than we imagine, but stranger than we can imagine. And it is in these unsolved problems, these persistent mysteries, that we find science at its most human, most humble, and ultimately, most magnificent. For every solved problem reveals 3 new mysteries, ensuring that the adventure of discovery will never end. Music fades out, total word count, 1805 words.